morning, everyone. I hope you are all doing well. I am Professor Amar Kumar De. I hold the position of Associate Professor in the Department of Electronics and Telecommunication Engineering at BIT Durg. My area of expertise is in digital electronics and circuit design, which is precisely what we will be exploring into today. I am really excited to be here with you today to explore the fascinating worlds of encoder and decoder. These are fundamental components in digital electronics, and by the end of this lecture, you will have a solid understanding of how they work and their applications. But before we dive in, let me outline what we aim to achieve during this session. The aim of this lecture is to provide a comprehensive understanding of encoders in digital electronics. We will explore the principles of encoder and decoders, discuss the different types of encoders and applications of encoders with a focus on 4 input and 2 output, then 8 input, 3 output and decimal to BCD encoders, which has 10 inputs and 4 outputs. By the end of this lecture, you will have a clear grasp of how encoders function and their significances in various electronic systems. With this aim, we can proceed to cover the contents of today's lecture. The titles of the today's lecture is Encoder and Decoder. The lecture flow will be, it includes the historical evolutions of encoders and decoders, their basic principle, types of encoders and their real world applications. First, let's explore the historical evolutions and development associated with encoders and decoders. The development of encoders and decoders in digital electronics is noted with the bordered history of digital computing and the evolutions of electronic components. Let's explore the key historical milestones associated with this device. First is the early digital computing, starts from 1930s to around 1940s. The history of digital electronic can be traced back to 1930s with the invention of computer. Pioneers like John Athenshoff and Alan Turing contributed to the conceptual foundations of digital computation. During this period, computer primarily used mechanical switches and vacuum tubes for data processing. These early machines need devices to encode and decode binary information. Then the second historical event was emergence of the binary encoding in around 1940s. Binary encoding, representing information as a sequence of zeros and ones, become fundamental to digital computing. It was essential for encoding data for processing in early computers. The need of efficient way to convert between binary and other forms of data representations led to the development of early encoders and decoders. The third historical event is the introduction of integrated circuit in around 1960s. In 1960s marked a significant advancement with the introduction of integrated circuit ICs. This tiny silicon chip could perform various logical functions, including encoding and decoding. ICs allows for the creation of compact and reliable encoders and decoders, making them more accessible for a wide range of applications. The next historical landmark is the evolution of digital electronics. The 1970s and 80s witnessed the rapid expansions of digital electronic in various industries, including telecommunication, computer and consumer electronics. Encoder and decoder played a pivotal role in data communication, error correction, remote control system and memory addressing. Another important landmark in historical evaluation and development associated with encoders and decoders is the standardization in digital technologies. As digital technologies continues to advance, standardization efforts such as the development of industry-wide code standards and communications protocol further enhance the use of encoder and decoder. This device found applications in areas like data compression, multimedia encoding, secure communication and signal processing. The next event is the integration into microcontroller and programmable logic controllers. It started in around the year 2000 with the production of microcontroller and programmable logic device. Encoder and decoder become integral component in this system. Today, they are found in a wide range of electronic devices from smartphone and smart appliances to automotive system and industrial automations. Next, the ongoing advancement are the field of digital electronics is continuously evolving and ongoing advancement in encoder and decoder technologies are in progress. Emerging technologies like quantum computing may introduce new encoding and decoding challenges and opportunities in the future. In summary, the history of encoders and decoders in digital electronics is closely tied to development of digital computing and the need to efficiently process and communicate binary data. These devices have evolved from early mechanical and vacuum tube based solution to modern integrated circuit, enabling a vast era of application in our digital world. Their importance in digital system continues to grow as the technology advances. Now, let us understand what is an encoder is by first defining it. So, an encoder in general is an electronic device or a digital circuit that is designed to perform the functions of converting one form of data or signal into another, typically with a goal of simplifying data representation, transmission or processing. Encoder takes input data in a format and produce the output data in a different format, often in a more compact and structured manner. In context to digital electronics, an encoder is a combinational circuit that converts input signal into a coded output representation. It is used to compress or encode information from multiple input lines into a smaller number of output lines. The primary purpose of encoder is to provide a unique code for each combinations of input signal. The encoder output is generally a binary format where each output lines represent a specific input condition. So, let us say the input 2 to the power n are decimal and produce the binary code corresponding to its input value, the number of outputs will be n. Before moving ahead, let us spare few minutes in identifying some potential applications of an encoder. An encoder found its applications in data compression. One of the primary purpose of an encoder is data compression. Encoders are used to represent data in a more efficient manner, reducing the number of bits needed to transmit or store information. This is particularly important in applications like data transmission over network or storage in memory devices, where bandwidth or memory space is limited. Encoders are also very important in the areas of signal conditioning. In various engineering and communication systems, raw sensor data or signal may be noisy or in an unmanageable format. Encoders can condition the signal, converting them into a more usable and robust format. For example, in motor control, encoded signal can be used to precisely measure speed and position. Data encryption is another area where encoders are essential. Encoders are employed in encryption algorithm to transform plain text data into a coded or crypted form, making it difficult for unauthorized access to sensitive information. This is crucial for secure data in applications like online banking and communication. Encoder also found its application in memory mapping and addressing. Encoders used to convert memory addresses from a readable format to a format suitable for assessing specific memory locations. This simplifies the memory addressing process and enhance memory management. Next application is error detection and correction. Some encoders are designed to add redundancies to data, allowing for error detections and corrections during transmission and storage. This is essential in data communication and storage system where data integrity is critical. Another application is in communication protocol. Encoder plays a crucial role in communication protocol by encoding data in a standardized format from transmission over network. This ensures that data is transmitted reliably and decoded correctly at the receiver end. Next application is in digital control systems. Applications like robotics and automations, encoder are used to provide feedback on the position and speed of moving part. This feedback is essential for accurate control and feedback loops. In remote control system, remote control devices such as TV remote, encoders are used to encode the button pressed into a format that can be transmitted via infrared or radio wave to control electronic devices. In the areas of industrial automations, encoders are extensively used in manufacturing and industrial automation for precise measurement, control and monitoring of machineries and processes. Last but not the least, encoder can be found in various consumer electronics such as digital camera for optical zooming control, audio equipment for volume control, and in gaming for tracking movements. In summary, encoder serves a diverse range of applications in digital electronics, from data compression to encryption to error detection and control systems. They enable efficient data representation and communication, making them fundamental component in modern digital system. As we discussed the various applications of encoder, now let us together explore the different types of encoder in digital electronics. There are different types of encoder based on their design and functionality. Here are some common types. The first is the binary encoder. The binary encoder has 2 to the power n input lines and n output lines, where n is the number of select line. It provides a unique binary code for each input combinations. The most commonly used binary encoder is 2 to 4 line encoder. The second is priority encoder. A priority encoder is a variation of a binary encoder. It assigns priority to the input line based on their position when multiple input lines are active. Simultaneously, the priority encoder encodes the highest priority active input. It is useful in the application where a specific order or priority needed to be stabilized. Next type we have decimal to binary encoders. These types of encoders convert decimal input values 0 to 9 into their binary representations. It typically has 10 input lines and 4 output lines to represent the BCD, binary coded decimal code. We also have octal to binary encoder. An octal to binary encoder converts octal input values 0 to 7 into their binary representations. It usually has 8 input lines and 3 output lines. Finally, we have the priority encoders. These types of encoder is designed to encode only the highest priority active inputs, as already discussed. It ignores other lowest priority inputs. It is useful in applications where specific order is required. So, in this lecture, we will focus on binary encoder and their limitations. So, the binary encoder is the combination circuit with n output lines and 2 to the power n or lesser inputs. Its operation is precisely the reverse of the decoder. So, in case of the decoder, we have n input lines and 2 to the power n or fewer outputs, and as per the specific input combination, only one of the output is high. But in case of encoder, precisely the reverse happens. Moreover, in the encoder, it has been assumed that at any given time only one of the input is high, and depending on which input is high, we get the specific code at the output. So, let us take the case of 4 line to 2 line encoder and let us understand how this basic encoder works. So, as you can see, this 4 line to 2 line encoder has 4 input lines and 2 output lines. That means at output this n is equal to 2 and the total number of input is equal to 2 to the power n, which is equal to 4. And here is the truth table for this 4 to 2 encoder. So, as you can see, when the D0 input is high, the output of the encoder is equal to 0, 0. Likewise, when D1 input is high, then the output of the encoder is equal to 0, 1. Similarly, when D2 is high, then output will be equal to 1 0, and when D3 is high, then that output of the encoder will be equal to 1 1. So, in this way, this binary encoder encodes the input information into the compact code. So, now let us see the logical circuit for this 4-line to 2-line output encoder. As you can see from the truth table, output A is high when either D2 is high or D3 is high, which means the logical expression for this output A is equal to D2 plus D3. Likewise, output B will be high whenever D1 is high or D3 is high. That means the logical expression for this output B is equal to D1 plus D3, and these two logical expression can be implemented with the help of the OR gates. So, this is the logical circuit of this 4-line to 2-line encoder. Similarly, now let us see the 8-line to 3-line encoder. So, in this case of 8 to 3 encoder, it has 8 input lines starting from D0 to D7 and 3 output lines starting from A to C, and depending on which particular input is high, we get specific 3-bit code at the output. So, here is the truth table of 8-line to 3-line encoder. So, you can see when D0 input is high, the corresponding output code is equal to 0 0 0. Likewise, when the D5 input is high, the output code is equal to 1 0 1, and similarly when D7 is high, corresponding output code equals to 1 1 1. So, this way we get the specific output code corresponding to the individual inputs, and based on this truth table we can also design a logic circuit of this 8 to 3 encoder. As you can see, this output A is high and either D4 high or D5 is high or D6 is high or D7 is high. So, we can say that the logical expression of this output A is equal to D4 plus D5 plus D6 plus D7. Likewise, B is high when either D2 or D3 is high or D6 or D7 is high, which means that the logical expression for this B is equal to D2 plus D3 plus D6 plus D7. Similarly, the output C is high whenever D1 is high or D3 is high or D5 is high or D7 is high. So, we can again say that the logical expression of the output C is equal to D1 plus D3 plus D5 plus D7. In this way, you get the 3 logical expressions for the output A, B and C, and these 3 expressions can be implemented with the help of OR gates. So, this is the logical circuit of this 8-line to 3-line. So, as you can see, this binary encoder encodes the input information into the compact code. So, in this way, the encoder is particularly useful when we want to connect so many input devices to the process or the controller. For example, let us say you want to connect the 8 switches to the controller. Let us say each key represent specific symbol of specific actions. For example, let us say we are designing the gaming pads for some applications. That means whenever these keys are pressed, the input to the particular pin is equal to VCC, and in that case you will get the high input at particular pin, and when the switch is not pressed, then the input at that pin is equal to 0. So in this way the processor or the controller, or you can know that the particular key is pressed. So without the encoder, in this case we required the 8 such input output pins of the controller. Of course, nowadays the controllers comes with so many inputs outputs pin, but when we want to connect so many inputs to the controller, they might run out of numbers of input output pin. So in such case the encoders is very useful. So in such case what we can do, we can connect the 8 switches to the encoder, and the output of the encoder can be given to the controller. So depending on which key is pressed, we get the specific code at the output of the encoder, and by reading that code the controller can know which key is pressed. So in this case, instead of the 8 pins, we just required 3 pins, and in this way we can save the number of input output pins. So this 8 line to 3 line encoder which we discussed can also be used for octal to binary conversion. So in such case each input represents the specific octal number, and the output of the encoder is the binary code which is equivalent to that particular octal digit. So likewise we can also design the decimal to BCD encoder. Okay. So in the decimal to BCD encoder we have 10 input lines and 4 output lines. So here each input represents specific decimal digit, and the output is the BCD equivalent code corresponding to that particular digit. So here is the truth table of this decimal to BCD encoder. As you can see, corresponding to particular input we get the 4-digit BCD coded. That means whenever this D0 input is high, the corresponding BCD code is equal to 0000. Likewise, when D7 input is high, then the corresponding BCD code is equal to 0111, and similarly when this D9 input is high, then the corresponding BCD code is equal to 1001. So with the help of the truth table we can also design the logical circuit of this encoder. For example, this output A is high when D8 is high or D9 is high. That means the logical expression for this output A is equal to D8 plus D9. Likewise, this B output is high when this D4 is high or D5 is high or D6 is high or D7 is high. That means the logical expression for the output B is equal to D7. That means the logical expression of the output B is equal to D4 plus D5 plus D6 plus D7. Similarly, the output C is high when D2 is high or D3 is high. Likewise, the output C is also high when this D6 is high or D7 is high. So you can say that this logical expression of the output C is equal to D2 plus D3 plus D6 plus D7. Likewise, the logical expression for the output D is equal to D1 plus D3 plus D5 plus D7 plus D9. So this is the logical expression for the output D. So in this way we got the 4 different expressions for individual outputs, and each of them can be implemented with the help of the OR gate. So here is the logical circuit for this decimal to BCD encoder. In this way, we can implement any particular encoders. So now let us see few limitations of this normal encoder. So in case of normal encoder, we have assumed that at the most only one input is high, but when all the inputs of the encoders are 0 or when more than one input are high, then this encoder circuit will not work properly. And to understand that, let us take the case of this 8 line to 3 line encoder. So in the case of this 8 line to 3 line encoder, when the D0 input is high, then the corresponding output is equal to 0, 0, 0, 0, and that is also verified from the logic circuit, because here this D0 input is not connected to any of the OR gate. That means when this D0 input is high, all other inputs are 0, then the output of the 3 gates will be equal to 0, 0, 0. But suppose if all the inputs are 0, then also the output of this encoders will be equal to 0, 0, 0. That means for the two different input conditions, we will get the same output. So to resolve this discrepancy, we can have one more output to this encoder, which will indicate that at least one of the input to the encoder is high. So if all the inputs to the encoders are 0, in that case the output V will be also equal to 0. And when the output V is equal to 0, in that case it doesn't matter what is the other output of this encoder. So in this way, we can distinguish the condition when all the input to the encoders are 0. Apart from that, the other issue with this encoder is that if more than one inputs are high, then the output encoder will be invalid. Apart from this, the other issue with this encoder is that if more than one input are high, then the output of the encoder will be invalid. For example, if D1 input is high, then the output of the third OR gate will be high. If rest of the input to the encoders are 0, in that case the output of this OR gate should be equal to 0, 0, 1. Similarly, when D2 input is high, then the output of second OR gate will become high, and if the remaining inputs are 0, in that case the output of the encoder will be equal to 0, 1, 0. But suppose if both the input D1 and D2 is high simultaneously, in that case the output of the second and the third OR gate will become high, and if you see the overall output of this encoder, it is equal to 0, 1, 1, and this output indicates that the input D3 is high. But actually in this case the input D1 and D2 are high, and in this condition we are getting the invalid result. This means that the normal encoder will not work when more than one input to the encoder is high, and to avoid that we need to set the priorities to the input. For example, we can set the priorities like when more than one inputs are high, then the input with higher subscript will have the more priority, and in that case that input will be considered as high. So such encoders are known as the priority encoders. In the next session, we will take some basics of the priorities encoder and discuss the details about the decoder. With this, we come to an end of today's session. Before we conclude, I want to restate how much I appreciate your decision to learn and your enthusiasm for today's topic. Your presence has made my role as an educator incredibly fulfilling. Remember that learning is a continuous journey, and I encourage you to explore the topic further and discover the countless opportunities it holds. With that, I do like to thank you once again for joining me today. Your presence and participation has made this lecture a meaningful experience for all of us. I wish you all the best in your future academic pursuit and beyond. Thank you. Have a fantastic day ahead.